Hello, machine design students. We're going to be talking about Chapter 19, Fasteners. So, relatively short chapter. We're just going to talk about the objectives, a little bit about bolt materials and strengths, and a little bit about thread designation and what the stress area is for a threaded fastener. And then we're also going to talk about clamping load and tightening of bolts. Okay, so first terms I want you to think about is the difference between a bolt and a screw. The way the textbook defines this, the bolt usually goes through two members and has a nut attached to it, where the screw goes through one member and is threaded into the second one. Briefly, I want to talk about these bolt styles. These are just the basic types. I'm not going to talk about it too much, but you should know what you're looking at with these types of bolts. And these are cap screws or machine screws, and these are the different head configurations that are available commercially. Flathead screw fits into a countersunk hole. A button head, again, has a round button and it sits on top. Philister heads are usually bigger and more round, and then are recessed too. And then round head is a lot like a button head, except it's smaller. And then a socket head cap screw has a Allen wrench type of element for driving it. And then a flange head, all that really does, it has a bigger diameter, kind of like takes the place of a washer. So those are your basic cap screws. Bolt materials and strengths. We're not going to talk too much about bolts, the different types of materials, but we are going to talk about strength in terms of bolt grades. Really what you want in a fastener is you want high strength, you want high stiffness, and good ductility, and good machinability and formability. And then the strength of the steels used for bolts and screws determine its grade. This is the type of grade that we're going to be talking about the most here. This is the SAE grades. When you're talking about an SAE grade, you got grade numbers 1, 2, 5, and 8. And the way you can tell these just by looking at a bolt is by the number of marks on the head. So the grade 8 bolts look like this, the grade 5 bolts look like that, and the grade 2 doesn't really have markings on them. And then if you look at this value here, we know about tensile strength. Okay, that's the ultimate tensile strength. And we know about yield strength. We learned that in previous classes. But here we have a term called proof strength. A proof strength can be likened to the elastic limit on a bolt, and we're going to talk a little bit more about that. But as you notice, as you go up in grade number, you go up in proof strength and yield strength and tensile strength. So the higher the number of the grade, the stronger the bolt. Just for completeness sake, I want to talk about briefly ASTM grades. ASTM grades are a little bit different, and you'll find those listed kind of like this. I'm not going to talk about those. I'm not going to compare those back to SAE. We want to stick with the SAE for this discussion. And also metric grade bolts. Metric grade bolts have a grading system too. We're going to not talk about that. And then other materials for bolts. You can read through these slides, but we're going to be primarily focusing on steel bolts for this discussion. So typically we have the equation that we're going to be using in this chapter is stress equals force divided by area. We're very familiar with that equation. We know about that before. But when we're talking about bolts has a tensile stress area, so that you need to understand what the tensile stress area is for bolts. It's not like the diameter of the bolt, because the bolt has threads, so we need to compensate for the thread area that's missing. Table 19-4 really talks about these tensile stress areas. Okay, so here's our basic diameter. This would be the nominal diameter, and then this would be the size in the threads per inch. Okay, we talked about like a number 1024 is a UNC coarse thread, and number 1032 is a UNF fine thread, and this chart here tells you what the tensile area is based on what the thread pitch is and the basic size of the screw. So we're going to be using this table in the problems. Okay, so here is another table, and we got the same thing for metric threads, but we're not going to talk about metric threads. And then we're going to talk about clamping loads and tightening torque. Okay, we're going to talk more about that in the next video for the example problem. And the only thing I want to bring up now would be set screws. So most bolts and screws have enlarged heads that bear down on the part to be clamped and exert clamping force, but a set screw is headless. Typically, it's inserted into a tap hole and it's made to bear directly on a mating part, locking it in place. So we talked about, in chapter 11, we talked about keys, and we talked about shear pins for driving torque, where a pulley is mounted to a shaft. The set screw will do the same thing, but its ability to transmit torque is not as good, because in this case you'll have a flat point or a cup point. Cup point's meant to bear right on the surface, so you got to put enough torque on this thing such that the thread bears into the surface. And if the set screw were to loosen, then you're going to have your hub spinning on your shaft, and so it's not good. I want you to briefly review these types of points because that's one of your objectives. Okay, that's the end of this video. There's a second video that's going to be covering what we're going to do in the assignment problems for chapter 19.